Okay, so for this homework problem, we're looking at example 1.18, which is a multi-component steady-state gaseous diffusion example that has a chemical reaction. So this chemical reaction has ethanol that reacts into acetaldehyde and hydrogen gas. So what we have here is that we are given our mole fractions at one side of our system, but as we get to our boundary, to our interface, we don't know our composition there. Also, we're given, based on our equation, we have bootstrap conditions for our molar fluxes, and we are told that the rate of the reaction is based on the rate of reaction of ethanol. So that's why we have N1 equals the rate of reaction times the mole fraction at the boundary. So this question is asking us what the overall rate of reaction is. So first we'll start with the Stefan-Maxwell equations. So this Stefan-Maxwell equation here can be written out as this as our driving force of our first component and our driving force of our second component. So we can write this out in terms of eta. So eta tells us the ratio of z to our boundary layer. So it's a range between 0 and 1, and it lets us know in a more convenient way where we are along the system. At a value of 1, we would be at the interface. So it's also important for us to make an estimate of what our values are for the mole fraction is going to be, because we don't know a lot of variables. We have two independent equations, and then we have three unknown variables when we write it out in terms of our bootstrap conditions and our mole fractions being a part of 1. So it's important for us to make an estimate to find a scale. So we'll first start with this portion. So our boundary layer is expected to be a small value, so we're going to make the estimate that it's to a magnitude of 1. And then our concentration here, since it's a gas situation we're looking at, can be written as pressure over RT. So our pressure was given as 101.3 kilopascals. So we're thinking about it in terms of pascals, that would be to the magnitude of 10 to the 5th. Then our R value, our gas constant, is 8.314. So that would be a magnitude of 1. And then our temperature had 3 digits, so that would be 10 to the 2nd. And then our diffusivity coefficient for gases is 10 to the negative 5th. So this front value would be approximately at a magnitude of 10 to the 3rd. And then here our mole fraction, we know it's a fraction, so we can make the estimate of the magnitude being 10 to the 1. So that leaves us with our molar flux magnitude being 10 to the negative 3rd. So this gives us a general idea of what to expect as we go through our calculations with Python. So now moving on to the Python code for this example. The first step is to import the Python packages that we'll be needing. So we first import numpy as np, then we have the packages for us to make our plots at the end, and then we have the data that will allow us to solve an initial value problem here, and then also what will allow us to solve for roots. So this will come up as we walk through the code. So the first section of code here is where I'm defining the given variables. So the first three are diffusivity coefficients, which were given in the example in the problem. And then we have our pressure, our temperature, our gas law constant. And then here is the definition of our concentration because it's an ideal gas. Then here's where we're making our Y1 delta gas. And then we are defining our mole fractions at our initial point. Also here we have our delta, which is our boundary layer thickness, and then K is our reaction rate. Okay, so next we define our equation for dy. So this is what I walked through earlier with our Stefan-Maxwell equations. And so our Stefan-Maxwell equations are in terms of eta, our mole fraction, and then our mole fractions at our boundary. So here are the bootstrap conditions. So relating the molar flux of component 1, 2, and 3 to one another. And this N1 here is saying that our reaction of ethanol is equal to the rate of reaction of the equation times our D1 delta or Y1 delta. And then this part is the Stefan-Maxwell equation. So our dy1 and dy2, and we write out the equation here. So after we've defined our Stefan-Maxwell equations, we define the function of our mole fraction changing with position. So our y delta function is relating our mole fractions along our axis. So with that equation, we are calling on our dy function, and then we want to integrate that from 0 to 1 with our initial values to give us values of our y as a function. So now that we have a function for our mole fractions, we need to find where y1 and y2 equal 0. So we want to find the roots of this function. And this will, since we have 3 unknowns, this will allow us to find our molar flux by finding where our other 2 unknown variables are 0. So that's what this code is doing. So we're using our root function. We're saying that this is the function that we want to find the root of, and this is our guess of where we think that will be. So that's what this section of code is doing. And then we move here to our next part. And now we're finding eta, how our mole fractions are different at different etas. So this eta we are defining from starting at 0 to 1, because again, it's a ratio and we're looking at 11 different increments, so 11 different values from 0 to 1. And here we're defining what our z and eta relationship is. And we write out what this code is doing. We can see that this line of code is giving us, so y1, what it is at eta equals 0. Eta equals at each individual increment as we get up to eta equals 1. So where we are at the interface, so where z equals delta. So this, I just wanted to show that this is an array. And so y1 at the initial point is our given value, and then y2 at the other point would be our second value. So we want to find our rate of reaction. So for N1, we are looking at our K, our given value, which is of 10, and then multiplying it by our mole fraction at the boundary. So that's why eta equals 1 here with eta equals 1. So this inputs our mole fraction at the boundary. And from that, we get that our overall rate of reaction from the question is equal to 0.8878, and these are our mole fractions at that film boundary. And then here is the code to write, to display our mole fractions and how they're changing with the z, so what they look like when they get closer to